So maybe you've seen this formula for finding the location of the center of mass of a system of masses. I'm going to go through and derive it really quick. It's not that hard to derive this formula for finding the location of the center of mass. So we'll just start off. Let's imagine we have three masses. You could do this with arbitrary numbers of masses. It doesn't really change much in this derivation. We want to find the location of the center of mass. What does that mean? It means there's some point in this system. Imagine these masses were connected by a light, rigid rod. So imagine this rod has basically no mass. Significantly, it's negligible compared to the masses of these M1, M2, M3. But it's rigid enough that it holds them together. What that means is there's going to be some point, I don't know, I'm just guessing. Maybe it's like right here. Maybe this is the location of the center of mass. Now there's different ways to define center of mass. Probably the easiest way is to just think about it as if you put a pivot right there at the location of the center of mass, there's one point here where the system would be balanced. You could balance it right on that pivot, and if it balanced, you'd know that you put the pivot at the center of mass. So the center of mass is one location here. You put the pivot somewhere else, it's going to tip. So we want a formula for finding this. So the way we're going to derive it is just imagine we measure the locations of these masses M1, M2, and M3 from some arbitrary location over here. So again, you can measure from wherever you want as long as you're consistent. So I'm going to measure from here. You wouldn't normally want to do this. Normally you'd want to measure from like one of the masses to just make your life easier, but I want to derive a general formula. So I'm just going to let this be some arbitrary point over here. So mass 1 we'll say is x1 from this arbitrary location. Mass 2 is x2, and mass 3 is x3. And that means we're going to be measuring from here. Everything's going to be measured from this reference point. So this is just our reference point that we choose, and you can choose whatever reference point you want. I'm just going to choose this one. That means everything's measured from there, including the center of mass. So if we want to know how far is it to the center of mass, that's going to also be measured, and it goes to this tip, this point right here. This is going to be measured from that location as well. Everything's going to be measured from there. So how do we find the center of mass? Well, it's the location where the system would be balanced. Balanced means that the net torque about that center of mass has to be 0. That's what it means to be balanced. If net torque wasn't 0, well, that means this thing's tipping. It's going to angularly accelerate in one direction or the other. So we need the net torque to be 0. Torque equals 0. And what could we say? Well, these three masses all exert a torque. So you're going to have a downward torque. Well, I shouldn't say downward. You're going to have a clockwise torque right here. So you have M3, G, and then times a length. So if you remember the formula for torque is defined to be R times F, technically times sine theta. All of our thetas are going to be 90 degrees here. So sine of theta is just going to give us 1. So I'm going to leave those off. So it's going to be R times F. So mg is the F. We got a force of gravity. And we have times an R, but the R is not going to be x3. I can't do m3g times x3 here. That's not true because I don't care about the torque around this rando point here. I care about the torque about the center of mass. This is where I'm going to put my pivot. So if this is where the center of mass is, my claim is that the net torque around this point is 0. So I can't do x3 here. What I have to do is, you got to imagine this distance from center of mass to the center of M3 right there. This is the length I'd need to put in for R. So this is the R for torque. The torque for this gravity around the center of mass is going to be R. Well, what is that going to be? It's just x3 minus the center of mass. So this R value is, you imagine this entire length x3 from this wall or this random reference point to M3. If I subtract the distance from the wall to the center of mass, that gives me this distance here. So I'm just going to rewrite this as x3 minus x of the center of mass. So wherever the center of mass is, and we're going to solve for this in a minute. So I don't know what that is, I know, but we're going to solve for it, and that'll give us the formula. So this is the torque for M3. And again, the torque's measured from the axis it would pivot about, and that's why we're measuring from there to here, which is just x3 total distance minus distance from the center, from the wall to this pivot, this center mass point. And I do this for each mass. So this mass would also have a torque that would be M2 times G. It would also be x2 minus the center of mass. Now you might object, you might be like, wait a minute, but the center of mass is farther from this random reference point than x2 is. So I'm going to get a negative number here. X center of mass is bigger than x2. But that's good, because look, this mass 2 is going to be rotating counterclockwise. So this torque should be negative when I plug it in and add them all up. So you really can just say, okay, take all these values. Here you got another one here. This is m1 times g times, all right, its r, which is from the center of mass all the way to it. Its r is going to be x1 from the wall minus the center of mass. And again, that would be negative as well. That's okay, because both of these are exerting their torque counterclockwise. So I mean, I just guessed where the center of mass is. It doesn't matter. Let's say the center of mass actually ended up over here or something like that. Okay, well then this would come out positive. So it works out. If you just subtract the distance from this random point to the mass, if you take that and you subtract from it the location of the center mass, the torque works out. If it comes out negative, it comes out negative because it's going to be going counterclockwise. If it comes out positive, that meant the center mass was over here, and you're going to get a clockwise torque. These torques we're just going to add up now. So if I do sum of the torque, add up all the torques, I'm going to get m1 g times x1 minus the location of the center of mass plus m2g x2 minus the location of the center of mass, and then I'm going to get plus m3g, the location of that mass, minus the center of mass. You might object, you might be like, wait a minute, but some of these torques are going clockwise and some of these torques are going counterclockwise. Why did we make them all positive? That's what I was saying earlier. If you just take x2 minus x center mass, the sign here is going to work itself out. If this center mass ends up to the right of m2, you're going to get a negative value, which makes this point opposite torque compared to m3. If the center mass is over here on the left of m2, you'd get a positive value. These would both be, m3 and m2's torque would both be the same sign, and it works out. So the sign comes out here. We don't have to supply the sign out front. If we're careful in our definition here, the sign will pop out as it should pop out. And so we're going to set this whole thing equal to 0. And we can clean it up a little bit. There's g everywhere, so we can get rid of g. Doesn't matter. This would work on any planet. And now I'm just going to distribute. So let's just distribute. I'm going to have m1 times x1 minus m1 times x center of mass plus I'm going to have m2 times x2 minus m2 times x center of mass, and I'm going to have plus m3 x3 minus m3 x the center of mass, all equals 0. So let's compile like terms here. I've got xcm and a bunch of these terms here. So I've got m1 x1, and then I'm just going to add m2 x2. You can probably see the formula emerging here. I've got a plus m3 x3. So this term, this term, this term, and then I've got all these terms with x center of mass. So I'm going to factor out minus x center of mass. I'm going to factor out an x center of mass, and I'll have m1 plus, and I've got this m2, I've got this m3 plus m3 equals 0. Now you can probably see what's happening. I'm going to move this to the right hand side and then solve for x center of mass, and what I get is that m1 times x1 plus m2 times x2 plus m3 times x3 is going to equal x center of mass times the sum of all these masses when I add it to the right hand side. And now all I have to do is divide. Now if I divide this side by m1 plus m2 plus m3, and I divide this side, I'm going to divide this side by m1 plus m2 plus m3, I just get the formula for the center of mass. This is the formula for the center of mass. So that's where it comes from. Take m1 x1 plus m2 x2 plus m3 x3, divide by the total mass of the system. You get the location of the center of mass. Again, you derive it from claiming that the net torque around that center of mass has to be 0. So that's how this formula comes about. And you can see now, I mean, throw in as many masses as you want. This is you could probably see it just keeps going. I'd have more terms here. I'd just add dot, dot, dot. I'd have more terms here, dot, dot, dot. And it would just turn out to be, no matter how many you got, you'd follow this format for finding the location of the center of mass of a bunch of discrete objects.